And it was like, yeah, you don't want to. That's a sample from like this drug or something.
That's, I mean, just for laughs, I'd love to like do that, take a sample, just go up, grab, you know, a fish sample, and send it off to 23 and see what
If
they
they do, oh, that would be really fun.
Yeah.
I said, you're 20%, 20% Irish. Yeah, whatever. All right, let's see here. So, any questions on the homework? Other than you can't demonstrate.
I know what the question is. So curious.
And next time it'll just be completely bland. It's say, here's your mean, here's your standard deviation. Are they equal? And then I'll have people say, well, it's not in real life. You don't ever just do that. There's always some sort of application for it. Blame Alex. He overthought the question. All right. So we did sign test, right? We ended with sign test. We lucked out. We didn't lose out on any classes, right? All right. So we talked about z-test and t-test. Kind of distinguishing between the two, it all comes down to that standard deviation. It's population level, you use z-test. If it's a sample, then we use our t-test. Our t-test requires that our data are normally distributed. If it's not normally distributed, then we can't run the t-test because we'll make a mistake. We'll probably make a type 1 error, but we could also do a type 2 error, right? We'll make a mistake in our conclusions. If we don't have normally distributed data, then we have, I'm going to say, two main options. We're either going to do a sign test or we're going to do this bootstrap. All right? So the sign test works. It's okay. Compares the median, not the mean. In some cases, you may only want to compare the medians, in which case the sign test will work. But know that the sign test needs at least 5 samples. It's non-parametric, so we have less power, right? And we have our script. So, you know, I gave you that script, sign test here, right, where it'll actually give you the output. So when you run it, after you run the function and you have this built in, have this successful in R, then sign.test runs our sign test for us, gives us the output that says you just ran a sign test and here's the p-value, right? This is okay. But perhaps you really do want to measure the mean. Perhaps you looked at your sample and it is skewed. Definitely skewed, but we're still focused on mean. What can we do? Well, what we can do is a bootstrapped confidence interval. Why do we do bootstrapped confidence interval? Well, it's a bootstrapping because we are not normal, and we want our confidence interval to adequately reflect the data. How do we use this to compare the mean? Let's say this is a bootstrapped confidence interval. 95% bootstrapped confidence interval. Let's say that that's what we have. All right. This 95% is significant because we're looking at which range captures 95% of all of our data points. All right. So 1 minus alpha is typically 95% when we set alpha at 5%. Where did that alpha 5% come from? That was our cutoff. That was our cutoff for the p-values, right? As we said, if we fall in that 5% region, that rejection region, we will reject our hypothesis and conclude that means are different, or that our sample mean is different than that hypothesized mean. We're going to apply that same rule here with our bootstrap confidence interval. So if our value falls within this range, I'm going to say captured, falls or captured by this range, then we fail to reject our null hypothesis. And just as a quick guide, what is our null hypothesis? Our null hypothesis is that our sample mean is equal to our hypothesized mean. All right. Our alternative in this case will be that our sample mean is not equal to that hypothesized mean, because we're going to allow our mu to fall either above or below our confidence interval. If this hypothesized mean, if this mu is captured by our bootstrap confidence interval, then we conclude that our means are equal. If this confidence interval does not capture our hypothesized value, then we can conclude that they are not equal. Okay? This gives us 95% of the values here, and then outside we've got 2.5% below, 2.5% above, which gives us that alpha level of 0.05. All right? And this is how we're going to use our bootstrapped confidence intervals. Fortunately, this has pretty good power. All right? Any conclusion that we come up with from a t-test, as long as our assumptions are met, will be the exact same conclusion as we would get if we use these bootstrap confidence intervals. All right, and I'll show you some of this. I probably shouldn't stand in front of the camera. I just kind of thought, man, what if the camera's up in my face? So here's my R. I'm going to open up my R markdown again. I'm going to go back and let's see here. Z-test, Z-test. Draw a hand, vectors here. So I'm going to run this vector t-test with a vector of data, and I'm going to run this t-test again just so we have it. In this example, we were testing if our randomized vector had a mean that was equal to 31. Mu equals 31. All right. Now we generated our random data set from a normal distribution. If we did a QQ plot, we would conclude that, yeah, this vector is normally distributed. So we meet the assumptions of a t-test. In this output, it gives us this 95% confidence interval. All right. And as I said, if our data are normally distributed, then the parametric confidence interval, which is what this is, will be very, very similar to our bootstrap confidence interval. Bootstrapping, any variation is just due to the random nature. So in this case, when we look at the p-value, we can see that the p-value is less than 0.05. We would conclude that our mean is not equal to 31. Incidentally, check out this confidence interval. Does that confidence interval include the value 31? No, it doesn't. 31 falls outside of it. So if we just use the confidence interval comparison, we would conclude that, yeah, our means are different. This interval does not capture our mu. And this will always hold true. This will always hold true on all of our t-tests. So we can go down and here's our mosquito fish. All right, if I read them in, you can see it. We concluded that our mean did not equal 24.5. Well, here's the confidence interval. Does that include or capture 24.5? No. 24.5 fell outside of that confidence interval. Was pond 1 normally distributed? Yeah, it was. We concluded that it was. Pond 2, was it normally distributed? Yep, it was. All of our ponds were normally distributed. P-value was 0.06, 0.07. we concluded that the means were equal. Did the confidence interval capture 25.15? Yeah, just barely, but it did. It captured it. All right. Pond 3, no difference. Did it capture 25.05? Oh yeah, it captured it. We went from negative infinity to 25.1. And pond 4, 23.75. Check out our confidence interval. Does not include 23.75. Now you could ask, well, why does it include the infinities? It's because we set up direction. We said it could be greater or it could be smaller. All right, and we would have to account for that. And we could, with our bootstrapping, we could adjust where our 5% comes, which is what the t-test does. All right, but I'm going to say no. If we're doing our bootstrapping, we're interested. Are they equal or not? All right. If they're not equal, then we can conclude one is larger than the other. So how do we do our bootstrapping? We've already done our bootstrap confidence interval. We already have the code. So remember, our bootstrapping is done when we sample with replacement. And we set up our code. So here I created my randomized vector. That was going to hold the means. I used our means before. All right, and then I have my loop where we take our sample of our vector, we sample with replacement, and then we calculate the mean and save it, and so forth. All right. I'm going to be giving you a script in a minute here. All right, and then we talked about our interpretation. So remember, our sample mean is going to be equal to all hypothesized means that are captured by this bootstrap confidence interval. So any value that gets captured, we conclude that that's equal to our sample mean. Any value that is not captured by a bootstrap confidence interval, then we conclude is not equal to our sample mean. All right. The only downside of this is that there's no p-value associated with it. And again, somebody may say, hey, we need a p-value. I don't think I would, but anyways. So pond 1, let's check it out. All right. I do have a function. You have a function, and it is on our next slide. So here's our function, just like our signed out test function. This is a function that will do the bootstrap means for you, bootstrapping of the means, since that is typically what we're interested in. All right, so I'm just going to kind of step you through what each of these does. So bs.mean, that's the object that we're going to create. That's going to be our function. We defined it as a function, and we gave it options. So x, that's going to be our vector that we'll give it. N equals 1,000. That tells us how many bootstrap replicates we're going to do. And ci is 0.95. So these are the defaults. 1,000 bootstrap replicates, 95% confidence interval. That's our defaults. Inside our loop, first thing we're going to do is we're going to issue the na.omit function on our vector and save it as another vector, or save it as the same vector. Now, all of this happens within a loop, so as soon as we get out of the loop, our vector is the same. All right, it's normal. All right, but what we're going to do is look at each of our items. If we have missing data, we'll get rid of it. Why? It's because of the mean function. We didn't include the na.rm. We just want to go ahead and get rid of the missing data. It'll make things a little bit easier, make it run just a little bit faster. Are we going to notice the difference in speed? No, this thing will happen very quickly. All right, so once we removed all of our missing data, then what we're going to do is create an empty vector called bs_means. That's what I called. And then I have my loop. So for I and 1 to n, so n, the default is 1,000, we can modify it. The first thing we're going to do is we're going to sample. We're going to sample our vector with replacement, get a new vector called bs, and then we're going to take the mean of that vector and save the mean in row I. And then it's going to loop over and over and over again until we have n number of rows. Once we have that, then we're going to calculate our confidence interval. And the low and the high is written here to figure out our cutoffs to create the confidence interval that we asked for. So if we wanted a 95% confidence interval, this is going to calculate 0.025 and 0.975. So it gives us our 0.025 and 0.975, which is the 95% confidence interval. If we wanted a 99% confidence interval, we would get 0.005 for the low and 0.995 for the high. This is just going to convert it for us, so that way you can change the confidence interval with this function. And then finally, it will output the quantile that we want. So the low and high value that we want. All right? So the usage then is something like this, where bs.mean of our data vector, if it's in a data frame, don't forget to use data $, and then the variable name. Typically, you're going to run at least 10,000 replicates, so n equals 10,000. And typically, our confidence interval is 0.95, so a 95% confidence interval. But again, I've written it so that you can run at 99, you can run at 98, you can run at 90%. You can do a 5% confidence interval if you wanted, and it'll turn out properly. All right? So what you can do is get this copied into our function list. So I give you a few minutes to get that into our function list. And then don't forget, after you get it in there, run that function. Run it so that it creates the function bs.mean. And then when you're done with that, make sure you read in your mosquito data set, or mosquito fish data set, because then we will do our bootstrapping on all of those ponds. Did you get it in? Did you get it run? Yes. So, my R mark down. Let me scroll up. So I have a function section where I make my functions here. That way, at the very start, it's going to run it. Alright, so I have my sign.test, and then I put bs.mean below it. And I ran it, and you can see that now our functions include both the sign.test and the bs.mean. So it's run, and then I also ran my data input, or my import for mosquito fish. So this was my read.csv line. So I have the mosquito fish data set, and I've got pond 1, pond 2, pond 3, pond 4, and so forth. All right. And then I've got my bootstrapping. All right. So with all of our tests so far, I've just kind of went ahead and summarized what we're doing. So our null hypothesis is that our sample mean is equal to mu, or some other hypothesized value. All right, our alternate is that it's not equal. All right, and I also wrote our interpretation. So if mu is captured by our 95% confidence interval, then we fail to reject our null hypothesis and conclude that our sample mean does in fact equal that hypothesized value. If the mu is not captured by our bootstrapped confidence interval, then we reject our null hypothesis and conclude that our sample mean is not equal to that hypothesized value. We're going to use the bs.mean function to generate our confidence intervals. So here is pond 1. Notice that I increased it to 10,000, and I'm going to do a 95% confidence interval. How long do you think it'll take? Did you run it? Not yet? You didn't run it yet? Doesn't take very long.
You told me that the dollar sign was expected down here.
Did you read it in your mosquito fish? Check up in your environment, see if mosquito fish is up there. And yours might be a little bit different. So pond 1, I can't remember what we were testing. Pond 1. Let's do this. 24.5. Pond 1. 24.5. Does our bootstrap confidence interval capture 24.5? No, it's outside. It's outside. So just from this, we would conclude that our sample mean does not equal 24.5. You'll note that this is the same conclusion that we got from the t-test, which that will happen. As long as our assumptions of the t-test are met, we will get the same conclusions, whether we do a t-test or we do a bootstrap confidence interval. All right? So I did it at another time. Slide that over. So I get the same 24.71, 25.33. All right, so that's what I ran when I made the presentation. 25.33 is the same number. I was just slightly lower. That's just randomness. All right. So go ahead and do pond 2, 3, and 4 with our bootstrap confidence intervals. All right, and those are the means that we're testing against. All right, and just see, does our bootstrap confidence intervals lead us to the same conclusion as our t-test? right, you get it? Copy and paste, hopefully. So I updated it. We're actually doing bar X, comparing the means, not the median. So, and you can see with 10,000 replicates, it happens pretty quickly. So 25.15, that is captured by this interval, so we would conclude that our sample mean is equal to 25.15. This confidence interval captures 25.05, so we would conclude that our sample mean is equal to 25.05. Our last is 23.75, and that is not captured by our confidence interval, so we would conclude that it is not equal to 23.75. In fact, our sample mean is greater than that. Now, we kind of fudged a little bit because we didn't really do that 5%, right? The 5% all in one tail. We could, if we wanted to. It just kind of changes what we're looking at. So it would be more of like a 90% confidence interval. That'll give us 5% down at our lower end. But there's nothing wrong with doing a 95% confidence interval, especially when you have one sample and you're just comparing it to a given value. Our write-up, not much more to say than this. Sample mean is not equal to 23.75. At some point, you are going to have to report the bootstrapped confidence interval, or you're going to have to say that you're using these bootstrapped confidence intervals to assess significance. All right? That's about all we say. There's no test statistic, no degrees of freedom, no p-value. All right, so going back, this is a valid comparison. I just kind of demonstrated how, as long as our assumptions are met, then we're going to come up with the same exact conclusion as our t-test. Right? The real benefit of this is when we violate our assumption, when we violate the normality assumption, we can't run a t-test. This gives us a way to actually do it. This gives us a way to calculate or make this comparison. Our confidence interval will reflect our underlying distribution, and thus, if the interval captures a mean, we conclude that they're equal. If it doesn't, we conclude that they're not equal. For downside, no p-value. And again, some people may get upset because you're not reporting a p-value, and they feel like they've been cheated of looking at p-value. But it's completely legit. Questions? All right. So let me go to Blackboard real quick. Right. So you have next homework assignment posted. All right, so one sample test, that's what we did today. That's due later today. No one had a question over it. That gives you time to practice using PT and P-norm again. Calculate a p-value, and then we have one sample test in R. So I have an R&D file, and I have a series of CSV files, so 6 of them. Open that. Open it. Oh, here it is. One sample test in R. All right, so you're going to read in all your data. And this is going to be a little bit more involved for the homework because what I want you to do is to check our normality assumptions. All right, so I want you to check normality of our variables. All right, and then you're going to run the tests. And you're going to see that first two tests are t-tests. So we're going to run our t.test on that. You're going to check for normality. You're going to run a sign test. Check for normality, t-test. All right. Check for normality, perform a t-test, do a bootstrap confidence interval. All right. Question 6, sign test, and then bootstrap confidence interval. So we're always going to start checking our assumptions as we get into these tests, because that's always what we have to do first. Have to check our assumptions. If our assumptions are met, then we proceed with the test that we want to do. If they are not met, then we have to seek an alternative. And this is kind of setting you up to that process. I also have you giving a write-up. Make sure you focus on including all of the things that you need to include for our write-up. All right? So when is this going to be due? I didn't put a due date on there. When do you think we should have it due?
Like the open due date option.
Open due date option. Let me open up our next presentation. Take a look at that. Because that tells us a lot of what we're going to have to do. I think having it due on Friday, that gives you immediate time to practice, and we're getting into ANOVAs. So that way I know we're going to have some practice, because we're going to start ANOVAs today. We've got Friday and Monday lectures, and then I know there's going to be some practice. But I think what we're going to do is I'm going to make the official due date on 31st, November 2nd. And there it is. Due date, there it is. So it appears on your calendar. I had no idea that that happened, but it's there. All right. And as we are at it, let's check our syllabus, because I don't know when our next exam is. When is our next exam? The 9th. Okay, so the 9th. That's good. That'll give us time. So I think Monday would be okay. The ANOVA may be a little bit abbreviated in terms of how much time you have to complete homework, but I think you'll be okay. We'll be okay with it. All right. So due date for that is Monday. End of class. End of the day. So ANOVA. We did our next presentation. Started again. ANOVA and a t-test. What we've done is one sample test. That's what we've done. All right? And our sample is one continuous variable, or one discrete variable, I should say, one quantitative variable. What we're getting into is now having two variables. We have a quantitative variable, and we have some sort of qualitative variable or categorical variable. All right? Our options, when we have a categorical variable along with a quantitative variable, kind of depends on the types of variables that we're working with and which of these is our independent variable and which is our dependent variable. We're going to start with the case where our categorical is the independent variable and our quantitative is our dependent variable. If all of our assumptions of a parametric test hold true, then our options will be ANOVA and a t-test. All right, so here's our setup. We performed an experiment where we measured some variable for different groups. All right, that some variable is going to be our dependent variable. It will be a quantitative variable, something that was measured. Okay, so our dependent variable is the value of the variable as determined by a value of another variable. So our variable itself is dependent upon, or could be dependent upon, some other variable of interest. It could be more than one thing. Could pause the line. So it could be more than one thing. It could be two things. Could be three things. Who knows? But our dependent variable, is going, the value of it depends on something else. So this is where if we measured wing lengths of roaches in two different buildings, the wing lengths may depend on which building we collected our roaches. So our dependent variable is going to be that quantitative variable that we measured. The different groups part of it is our independent variable. Where we capture the building, the roaches, what building we capture them in, has no effect. They're not dependent on anything. It's just we capture them, we assign them to a group. All right, this could be a single level group, which would mean we're just working with a one sample test at that point. Sometimes it's two groups. Cabinet experiments 3. All right. Sometimes it's 3 or more groups, perhaps all buildings on campus. All right, so our independent variable doesn't depend on anything else. This will be our grouping variable, or what I call our grouping variable. The biological questions that we're often interested in is if this measurement variable differs between our groups. All right, and we can phrase that in any way we want. But the main gist is that we're interested in if does that measurement variable differ between our groups. Another way to phrase it is, does our independent variable affect the means? Does building in which these things live affect our overall wing lengths? It means the same thing, because if it does have an effect, then the mean of our groups are going to be different. So which either way gets across or gets to the same type of statistical question, which is the means are equal, that's our null hypothesis, or the means are not equal. Or at least one mean is not equal to the rest. Now, with our hypothesis, with our null and alternate hypothesis, we make the assumption that our groups represent a random and independent collection of our samples. All right? And it's all from a single population. So if we had this big population of roaches, we assume that that group label is just randomly assigned. And if they're randomly assigned, then our means of each of those are going to be equal. If it's not randomly assigned, if there's actually structure there, then we can have a possibility where our means are different. So how many groups are we working with here? If we have 2 groups, then we can run a 2-sample t-test. All right, because a 2-sample t-test is comparing means between 2 groups. We can also run an ANOVA in this case. All right. I'll have more to say about that in a little bit. If we have 3 or more groups, then we're going to run an ANOVA, or at least t-tests and ANOVAs, that's what we want to run. Why can't we run a t-test with 3 or more groups? Well, a t-test is only 2 groups, that's all it is. Why can we run an ANOVA with 2 groups? Well, because the ANOVA isn't restricted to saying you have to have 3 groups. ANOVA can have 2 or more groups. I actually prefer running an ANOVA even if we have 2 groups, because the way the ANOVA works, it's going to be a little bit more robust to violations of a normality assumption than the t-test itself. If all of our assumptions are met, we will conclude the exact same thing with the t-test and an ANOVA. But if we violate our assumptions, especially the normality assumption, ANOVA is going to be a little bit more reliable. And in general, ANOVA is going to be a little bit more reliable. That's why it's been used so much. It's robust to violations of normality. So what we're going to do is introduce you to the t-test. Why do I introduce you to a t-test if we're going to be running ANOVAs most of the time? As a preview, our ANOVA tests the assumption, or tests if our means are equal. The alternate hypothesis for an ANOVA is at least one mean is different from the rest. We don't know which ones. So if ANOVA says, yes, at least one mean is different from the rest, then we always want to go to that next step to figure out which mean is different. And one of our options to do that is to run a series of t-tests to figure out which means are different from the rest. So we're going to introduce these t-tests now, kind of give you a preview of how it works, and then we're going to move to ANOVA, focus on ANOVAs to compare our means, and only use our two sample t-tests as post hoc tests, and actually only in certain situations. All right? So our two sample t-tests, we assume is that both of our groups are just random samples of the same population. That's our assumption. And if that is our assumption, then it means that our null hypothesis will be the mean of group 1 and the mean of group 2 are equal. That's our null hypothesis. Our alternate hypothesis is that they're not equal. All right, we didn't set up direction. We're just, they're equal or they're not equal. If they're not equal, then we can assign direction after the fact. But we're not going to test, is one larger than the other? That is done by doing this, making this comparison or checking these hypotheses. All right? So if our null hypothesis is true, then we can do a transformation where we take the difference of the means and divide by the standard errors of our populations. And that would approximate a t statistic. Now, what's going on here? Well, think back to this. If our means are equal, then the difference of our means will equal 0. All right? So what we're going to do, if we take our means, each of our values, and subtract them, then we're basically going to be running a one-sample t-test to see if the difference of our means is equal to 0. That's what this is. The difference of our means, d, minus our hypothesized value of 0 is this. But then we have to divide it by the standard error. And our standard error in this case is this SP times the square root of 1 over n1 plus 1 over n2. All right? SP is our pooled sample standard deviation. All right? It's basically the standard deviation of our entire data set. We ignore the groups, and then we scale it by our sample size. But this is kind of representing like a weighted average because we account for the fact that our samples may have different sizes. Do we have to worry about knowing this? No, we don't, because R will do it for us. R will do this for us. What about degrees of freedom? Degrees of freedom is equal to our sample size minus 2. So if we did a one-sample t-test, what is our degrees of freedom? The sample size minus 1, right? Well, the same thing applies here. Sample size minus 1 plus our sample size minus 1 gives us total sample size minus 2. All right, so with our t-test, our assumptions are these. Data are random and independent. Data are normally distributed within each group. All right, that's an important one. Data are normally distributed within each group, and the variances of our groups are equal. So we're going to have 3 assumptions. Random and independent, that's fixed by how we collect our data. We're not going to check that. But we're going to have to check both of these assumptions before we proceed with the t-test. So what we're going to do is we're going to stop here, and we're going to start with this t-test. I'm going to quickly show you how to do a t-test without checking these assumptions first, because our ANOVA has the exact same assumptions. And what we'll do is I'll show you how to check these assumptions in our ANOVAs, or in our introduction to our ANOVAs. All right? So don't forget the homework that was due today. I'd say go ahead and work on doing these one sample tests in R. Become familiar with using t.test, and then what we'll do is we'll pick this up on Friday. Sorry, that's the rest of the slide.